In the previous lecture we have derived the decomposition method. The method can be used for finding the solution of a system of linear algebraic equations, or we can use it for finding the inverse of a given matrix. We have also mentioned that the decomposition method can be simplified if we can use the property of the given matrix. Now let us take this particular case when the matrix given matrix A is a symmetric matrix. The method in that case has some special names. The method is called the Cholesky method, or it is also called the square root method. The method was actually derived in two different places at the same time, that is why the different countries. So that is why the names of Cholesky has come and the square root methods have come, but they have been actually been derived almost at the same instant of time, almost the published was around the same time. Now we start with assuming that A is a symmetric matrix. A is a symmetric matrix. Then we decompose A as A is equal to L into L transpose, or as A is equal to U into U transpose, where L is our lower triangular matrix and U is an upper triangular matrix. Any one of these decompositions can be used, L L transpose or A is equal to U into U transpose. Now if A is positive definite, then this decomposition is always guaranteed. So if A is positive definite, this decomposition is always guaranteed. As in the case of the LU decomposition method, this condition is a sufficient condition and not a necessary condition. So this is a sufficient condition. Now suppose that we have now decomposed A as L into L transpose. How do we use it further for the solution of problem? So let us take the case and illustrate for A is equal to L into L transpose. So the first was we said that we can solve a system of equations or we can find inverse. So let us try to use this to solve the system of equations Ax is equal to B. We follow the same way as in the LU decomposition. So we would write this as L into L transpose of x is equal to B. Then we shall denote this inner, the product inside, denote L transpose of x as some z. Then this will read as L into z is equal to B. Then we shall say that we first solve the second set of equations, solve Lz is equal to B. Now L is a lower triangular matrix, therefore this can be solved by forward substitution. This can be solved by forward substitution. Then we solve the first set, that is Lx is equal to z. L is a lower triangular matrix and therefore its transpose is an upper triangular matrix. So this will be an upper triangular system. Therefore we shall use the back substitution for solving this method. So use back substitution. Now again, as we have shown that we can solve here also by one forward substitution and one back substitution, but the advantage will be not to use this, but to use a slightly different procedure, and that is we can have an alternative between these two as, let us write down the first one, take in L inverse of this. So, I can write this as Z is equal to L inverse of B, I will take this as L inverse of B, and the second system I will write X is equal to L transpose inverse of Z. We know that transpose and inverse can be interchanged. So, this will be equal to L inverse of transpose of Z. Therefore, I need to determine only one inverse. L inverse is here, L its transpose is being used here. So, I need to determine only L inverse. Therefore, only L inverse is to be determined. Now, we have already shown it earlier that if L is lower triangular, its inverse is also lower triangular. Therefore, I can use the forward substitution to get the inverse of L also. Therefore, L inverse will also be obtained by using the forward substitution only, and we can then use the same L inverse in both the places and get the solution of the problem. Now, let us see how we are going to get the decomposition as A is equal to L into L transpose. So, let us write it down. Our A is equal to L L transpose. So, let us write down the full system A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN, L is a lower triangular matrix. So, let us take it as L11, L21, L22, Ln1, Ln2, Lnn. And we are multiplying by its transpose. So, I can just transpose it and write this as L11, L21, Ln1, that is the first column becomes the first row, and the second column L22, L2n, and so on. I will have Ln n over here. Now, let us multiply it and then compare the coefficients. So, if I take the first row and the first column, I will have L11 square. So, what I have here is L11 square is equal to A11. Therefore, L11 is equal to square root of A11. Now, I complete the multiplication of the first row and the other columns. So, L11 into L21, L11 L21 is A1, A2, A1 2. This is the product of this and this, and here A is symmetric. A is symmetric we have taken. Therefore, Aij is equal to Aji. Therefore, A12 is equal to A21, A1n is An1, and so on. So, these will be elements, will be the identical elements here. So, that we have here A12 is equal to A21, etc. Therefore, L11 into L21 is equal to A12. So, I can get L21 from here as A12 by L11 from this, and so on. The first row and the last column will give me L11 Ln1 is A1n. Therefore, Ln1 is A1n upon L1. Therefore, the entire set can be simply written as Li1 is equal to Ai1, this is your A1 A1i by L11. This is L21, L31, Ln1 is A1n by L1. So, this is our the first column of L that we have obtained from here. Now, we go to the second row. second column, because we do not need to multiply the first row because symmetric, so it is not necessary. So I will take the second row second column, that is L21 square plus L22 square, that will be equal to A22. So I will then have L21 square plus L22 square, that is the product of this second row second column is A22. Therefore we take to this side and take the under root of that. So I will have this as square root of A22 minus L22 square. L21 square. Now it is here we mentioned that if A is positive definite, our decomposition is guaranteed. If A is positive definite, this quantity is always strictly greater than 0 if A is positive definite. A is positive definite. Positive definiteness would imply that your A22 L21 square is always strictly positive. Therefore this under root sign, when it is coming, we are now doing the entire arithmetic in real arithmetic. But if you are going to complex arithmetic, it will not, it is okay, because then it is a negative number, then its square root will be a complex number, but we are doing real arithmetic. Therefore I would like to have real values only. Therefore this should be a positive quantity. Now if this will be positive quantity, is if A is positive definite, this is always guaranteed for us. Therefore in other cases this may turn out to be a negative quantity, wherein the method would then fail. Now we proceed on and then compute all the other coefficients. I can now write down, if you can see the diagonal element first, you take any row, multiply by the corresponding column, say ith row and the ith column, then it will be Li1 square, Li2 square, so on Lii square. That means I would get from here immediately that Lii is under root of Aii minus of your Li1 square plus so on Lii minus 1 square, or we simply remember it easily so that we can put this in summation notation, j is equal to 1 to I minus 1, that is your Lij square. Therefore these are all the squares, as you can see, of the all the previous available elements. So we are now on the diagonal element, so we are now taking the squares of all the previous elements, that is this particular component here, that is subtracted from Aii. That gives me all the diagonal elements, I is equal to 2, 3, so on n. Now the other elements I will now multiply by the method of matrix multiplication of this. Therefore I can immediately write down that Lij is equal to the same. So you can see that all these off diagonal elements would have a division by the its pivot. So the particular pivot, first row we are doing it is L11, second row we will be doing L22 and so on. If you are doing the Lij, that you will have your Ljj. So we will have here division by Ljj and you will have here Aij minus summation. This does not have any square roots, so it will be simply k is equal to 1 to j minus 1, again Ljk Lik. All the elements above, that is I is equal to j plus 1, j plus 2, so on k, and of course j is equal to 1, 2, 3 n. Of course in this summation, when the upper suffix is smaller than the lower suffix, then that summation is ignored, there will be nothing there. For example, if I take j is equal to 1 here, I will get here summation 1 to 0, so it is, there is nothing is there. Therefore that will then land in that particular case, will land into this particular case, this will land into the first one. So if I take j is equal to 2, then I will start getting the next elements that we will getting here. So this is the general loop under which all the elements of Lii and Ljj can be obtained. Now you would notice why the method was given a square root method. We have got square roots for each pivot, so all the pivots are to be done by square root. Therefore there we have got n square roots are to be used, n square roots are to be obtained from here. Now let us illustrate this by an example. So I will try to find the inverse of a matrix. Find the inverse of the matrix. Find the inverse of the matrix 4 2 1 2 3 2 1 2 2. Right. Let us also write using Cholesky method. So let us just write down the 3 by 3 matrix again 4 2 1 2 3 2 1 2 2. The lower triangular matrix L 1 1 L 2 1 L 2 2 L 3 1 L 3 2 L 3 3. We have this as L 1 1 L 2 1 L 3 1 0 L 2 2 L 3 2 0 0 L 3 3. Let us simplify it right here. Let us multiply it out L 1 1 square L 1 1 L 2 1 L 1 1 L 3 1. So we will have L 1 1 L 2 1 L 2 1 square L 2 2 square, then we have L 2 1 L 3 1 L 2 2 L 3 2, that is the product of second row third column. Then we will have L 1 1 L 3 1, then you have here this L 2 1 L 3 1 plus L 2 2 L 3 2, that is second this third row second column, and lastly we will have L 3 1 square L 3 2 square L 3 3 square. Now given matrix is symmetric, our L we have written it is L and L transpose, therefore these will be symmetric also, therefore this element has to be this element will be this, and this element will be this, because of the structure of the symmetry that we have used here constructing L and L transpose. Now I just compare these elements and write down the solution of these elements. So we will have here L 1 1 square is equal to 4, L 1 1 square is 4, therefore we have L 1 1 is equal to 2. Then the next element L 1 1 L 2 1 is equal to 2, given 2.
So why are you taking only positive, like why not minus 2 L 1?
When we are talking of a square root, we will be talking only of the positive square root. Either you use right throughout the positive square root or you use throughout negative square root. I can also use the negative square root, it would also give me the same solution. So either we are using either as positive root, but it is conventional to use square root as a positive square root. Therefore we have L 1 1 is equal to 2, therefore L 2 1 is equal to 2 divided by 2, that is equal to 1. Then we have the third element L 1 1 L 3 1 is equal to 1, therefore L 3 1 is equal to 1 by 2. L 3 1 is equal to 1 by 2. Now the three elements have been determined, the first column has determined. Now I go to the second. So we will take the middle element L 2 1 square plus L 2 2 square, that is the second pivot is given as 3, second pivot is 3. Therefore let us find out L 2 2 square from here, that is 3 minus L 2 1 square, L 2 1 square is 1, therefore I have 2, therefore L 2 2 is equal to root of 2, L 2 2 come here root of 2. Then we go to this last element L21, L31, L22, L32, and that element is given to us as 2. Now let us substitute the values. L21 is 1, L31 is half, L22 is root 2, L32 to be determined, that is equal to 2. So I can take half to this side, which produces 3 by 2, therefore L32 is 3 by 2 root 2. Then the second column is complete. So we go to third column, that is the third element. So we will have to take the last element over here, that is L31 square, L32 square, L33 square is given as 2. Now let us substitute the values. L31 square is 1 by 4, L32 square is 9 by 4 into 2, that is 8, plus L33 square is equal to 2. So let us take this to the right hand side. We will have this as 11 minus 11 by 8, that is 5 by 8. Therefore we have L33 is root 5 by 2 root 2. So all the elements are now determined. Now let us substitute the elements and then write down what is our L. Therefore from here I can write down the matrix L as 2 0 0 1 root 2 0, that is L22 is root 2, L22 is root 2, and this is 1 upon 2 3 upon 2 root 2 root 5 upon 2 root 2. Now what is it we want? We want the inverse. We have written A is equal to L into L transpose. I invert it, so I will write down A inverse is equal to L L transpose inverse. Now in inverting the product, it gets interchanged, L transpose inverse into L inverse. Now transpose and inverse can be interchanged, so I will write down L inverse transpose L inverse. Therefore our A inverse is simply L inverse transpose L inverse. Therefore I need to get L inverse and then transpose it here and multiply to get my A inverse. So L is lower triangular, therefore its inverse is also lower triangular. Therefore I will use the idea that L and inverse must be equal to I, product should be equal to identity matrix. That means I would have, let us write down our L and L inverse. So we will have here 2 0 0 1 root 2 0 1 by 2 3 by 3 root 2 root 5 by 2 root 2 into L inverse. Now let us call this as L11 some dash 0 0, L21 dashed, L22 dash 0, L31 dashed, L32 dashed, L33 dash. So just denote the elements by the dash terms. This must be equal to I, therefore this must be equal to this. We can make one observation, some of the elements are trivial because this is a lower triangular matrix, the same is true for upper triangular also. The diagonal elements of this will be inverse of the diagonal elements, in fact we do not need to compute them. L11 dash has to come as 1 by 2, L22 dash will be 1 upon root 2 and L33 dash will be 2 root 2 by root 5. But of course in our computation we can proceed on, but that will be a check for whether we are doing it correctly solution or not. So, these elements are trivially known. Therefore, that we can see if I multiply the row by this column, what I am getting is 2 times L1 prime is 1, that is your this element. Therefore, L11 dashed is equal to 1 by 2. So, this is the element that is true. Then we multiply the second row and the first column. So, that I will have L11 dashed plus root 2 L21 dashed. I multiplied the second row first column, that should be equal to 0. So, this should be equal to 0. Therefore, L21 dashed, now L11 dash goes to the right hand side. So, I will have minus 1 upon 2 root 2. Second row second column it just gives you root 2 into L22 dashed, that is equal to 1, this pivot. So, L22 dashed is equal to 1 upon root 2. The observation which you have made, the diagonal element will be of this will be inverse of this, that is 1 upon root 2. Then I can multiply this row and this column. So, I will have half L11 dashed 3 upon 2 root 2 L21 dashed plus root 5 by 2 root 2 L31 dashed, that will be this element 0. Now, let us substitute these elements here, that is equal to half into half, that is equal to 1 by 4, 3 by root 2 L21 dashed is minus 1 upon 2 root 2, and this we retain it as this 2 root 2 L31 dashed is equal to 0. So, let us take everything to the right hand side and get the element L31 dashed, that is 2 root 2 by 5, that this factor I have written it first, and then this will be minus 1 by 4 plus 3 by 8. Right, that gives us 2 root 2 by root 5, and this is equal to 1 by 8. So, that is equal to root 2 by 4 root 5. Now, we have determined the element L31 dashed. Now, to get the next element I need to multiply this third row with the second column. So, if I do that, I would get here, I am just writing this third row and the second column, that gives you 3 upon 2 root 2 L22 dashed plus root 5 by 2 root 2 L32 dash. I just have a look at this here, we are multiplying this row this column. So, what I would get here is 3 upon 2 root 2 into L22 dashed plus root 5 upon 2 root 2 L32 dash, and this element should correspond to this, that is equal to 0. Therefore, we can find out L32 dashed, that is equal to minus this factor, let us write it first, 2 root 2 divided by this 3 upon 2 root 2. No, oh, this is right, 3 root 2 upon L22 dashed, I have to multiply by L22 dashed. L22 dashed is equal to 1 upon root 2, that is equal to 1 upon root 2. Right, this is a factor I have written, this 2 root 2 upon root 5 written it, and this one. So, this gives us minus 3 by root 5, 2 root 10 into root 2, let us write it root 10, right. Or let us write it as 3 root 2 by 2 root 5, 2 root 5. And lastly, we have the product of this row and this column. So, that will be simply, which is I said trivially it is true. So, you will get it as 2 root 2 by root 5. the inverse of this element, Therefore, we have determined our L inverse. L inverse is equal to L11 dashed, that is equal to 1 by half. I will just write these elements 1 by 2 0 0 minus 1 upon 2 root 2 1 upon root 2 0 root 2 by 4 root 5 minus 3 root 2 by 2 root 5 and 2 root 2 by root 5. So, this is our inverse. Now, I write down the solution of the problem as A inverse is L inverse transpose into L inverse. So, I will invert this and write it as first matrix, that is equal to 1 by 2 0 0 minus 1 upon 2 root 2 1 upon root 2 0 root 2 by 4 root 5 3 root 2 by 2 root 5 2 root 2 by root 5 I should have written the transpose of the matrix L inverse. Let us avoid writing one extra step. Let us now write the transpose of L inverse. So, 1 by 2 minus 1 upon 2 root 2 transpose of this root 2 upon 4 root 5 0 1 upon root 2 and the 3 root 2 by 2 root 5 0 0 2 root 2 by root 5. This is our L inverse of transpose, and then this matrix I will write here this matrix half 0 0 minus 1 upon 2 root 2 1 upon root 2 0 root 2 upon 4 root 5 3 root 2 by root 2 5 2 root 2 by root 5. So, this is the matrix I will write it over here. Now, it is a simple very simple thing to just multiply it out and simplify it. I will give the value for this. So, the value that comes out is this, that is simply equal to 2 by 5 minus 2 by 5 1 by 5 minus 2 by 5, this is symmetric, it will come as 1 by 5 7 by 5 minus 6 by 5 minus 6 by 5 8 by 5. This is obtained by just multiplying the two matrices that we have given there. Now, the application of this would be that you are determining the inverse in a particular problem, and if you have more than one right hand side, this will be advantageous for us to find the inverse. We are finding only one L inverse in this particular procedure. Now, these two direct methods, that is the LU decomposition method and its version, that is the Cholesky method for symmetric matrices, and the Gauss elimination, are the most powerful methods that are used in our software. Even though there are more variants of the decomposition procedure than the Gauss elimination procedure, but even today these are the most powerful methods for solving the system of equations when the system of equations is small. If the system is too large of millions of or lakhs of equations, we just cannot load them on the computer. Therefore, there is no way that we can use these direct methods to solve such huge systems. But there are also some other practical problems in which let us try to solve a practical problem like this, that you are solving a particular problem within a given domain by a finite difference method, some set of differential equations. It gives you a system of linear equations. Let us assume it is a linear equations. Now, you find that the region that you have taken is not sufficient, you want to have a bigger region. Now, the region is now made bigger. Now, you again solve by the same method, you produce again a system of algebraic equations. Now, the idea is, can we use the computation that has already been made. That means you have solved this system of equations through decomposition. Let us say you have available A inverse for the a system. Now I solve the problem by extending that problem further. Can I use this computation that has already been used to rather to waste these computations? Can I use it? The answer is yes. The particular application is in fluid mechanics, wherein the condition for solving a particular differential equation is given as a condition like as x tends to infinity it should have this value, right, u tends to u naught, something like that, the velocity tends to u naught. So a condition as going x tending to infinity is given to us, but infinity is not defined in a particular problem. The infinity could be 9 in problem, in another problem it could be 100, it could be something else. So you want to solve it numerically, so you have fixed a finite length for that, say some 10 or so. You find that you have not achieved, that u is equal to u naught has not been achieved in the problem. So you have not positioned your infinity properly, so we have to move the infinity further. So infinity could be achieved 15. So now you solve the problem. What happens, the resultant is that the original system of equations stays as it is. If you look at the rows and columns of Ax is equal to b, what we really done is we have added few rows and few columns to the original system and got a new system. Now the idea is we want to use the inverse that has been determined earlier in the previous problem to solve the current problem and reduce the tremendous amount of computations. That is one application. The other application that we would have is, suppose we have a system of 100 by 100 equations is to be solved. Now would I prefer to solve 250 by 50 system of equations and some more computations rather than using a 100 by 100 system. We are going to show a little later that the computational effort for the Gauss elimination or the decomposition is order of n cubed by 3 for n large, n sufficiently large. That means if I solve the problem 100 by 100 and I solve a 50 by 50, the amount of computation is at least of the order of magnitude of 4 times. So if one problem takes 2 minutes, the other problem could take somewhere 6 to 8 minutes. So the order of the time that is taken up by doubling a system is much higher. Therefore what I would prefer in that case is I would like to use, if possible, the smaller systems, and in that direction we have what is known as partition method, which will partition our matrix A and obtain the inverse of this matrix using the inverse of the smaller systems. So what we mean here is like this. So let me call this as partition method. This, as I said, this has got very important applications in many areas of engineering. So what we do is, given this matrix A, I would conveniently decompose it, separate them as partition as this, and then name this as some matrices B, C, D, E. Now let us take A is a n into n matrix, A is n into n. So I can take B is equal to some R into R matrix, B is R into R matrix, and C is same rows, therefore R into S we will take, C is R into S, D is equal to S into R, E is equal to S into S. So that R plus S is equal to n, R plus S is equal to n. So this is the R rows, S rows here, and similarly the columns here. So these two matrices B and E are square matrices and these are rectangular matrices. This is R into S, this is S into R, but this is R into R, S into S. These are square matrices and these are the square matrices, and these will be rectangular matrices. Now what its application is, we are saying, suppose you have a system of 100 by 100. I want to have a let us say a system like this. So I could decompose, if it was given it like this, I can take 60 by 60 here, I can take a 40 by 40 system here, the two square matrices, then this will be 60 by 40 and this will be 40 by 60. Or I could as well decompose it as as 50 by 50, all will be square. I can decompose it as 50 by 50, 50 by 50, 50 into 50. Now what we were trying to say here is that if I want the inverse of this 100 by 100 matrix, I would like to utilize the inverse, known inverse, for example of this 50 by 50 matrix, or I know the inverse of 60 by 60 matrix, and thereby the amount of computation is reduced tremendously. Now in this case what we would do is we would also partition A inverse also in the same way. So partition A inverse also, partition A inverse also. So let us write A inverse is x, y, z, v. Partition also A inverse as z and v, so that the dimension of x and b are the same. So dimension x and b are same. So similarly your E and V dimensions will be the same, and the your C and Y dimensions will be the same, and D and Z dimensions will be the same. That is your, this is your R, and we have taken this as R into R, we have taken this E and V as S into S, this is C is R into S, this is S into R. Now it is straightforward. So what I would therefore write is, I will take that A inverse should be equal to I, A inverse is equal to I, and this I will also partition it as I1 I2. This I will partition as I1 is of dimension R into R, I2 is of dimension S into S. So I will partition it also into two identity matrices I1 and I2. This will be the same dimension of our x and b, and I2 will be the dimension of v. Now let us put the values of A and A inverse, that is B C D E x y z v, and this is equal to I1 I2. Now let us just multiply it out, the two matrices, there is matrix multiplication. So I will have B into x plus C into z is I1. So let us just number it 1, then B into y plus C into v is null, these are all null matrices, this is null matrix. Let us number it as 2, then D into x plus E into z is null. So we will have D into x plus E into z is null. Then the last equation is D into y plus E into v is equal to I2. Now we have assumed that the inverse of the B matrix, that is the one of the inverses is available for us, either the inverse of B is available or inverse of E is available. So let us start with, because there is an application oriented problem, let us assume inverse B exists and we know. So let B inverse be known. Now it is simply to solve these 4 equations for these 4 unknowns. So since B inverse is known, let us start with equation 2. Let us start with equation 2. I pre-multiply by B inverse, pre-multiply by B inverse. So this gives me B plus y plus B inverse C V is null. I have pre-multiplied this by B inverse. So y B inverse C V is equal to 0. Now I eliminate eliminate y from 4 using this. So what I have to do here is I multiply this pre-multiply by d and subtract from here. So what I will do therefore is I will take 4 equation minus d into equation 2. I have subtract the this, let us call it as 5, call it as 5. From 4 I will pre-multiply this by d and subtract from there. What does that give us? I have multiplied. From this I am subtracting, that is equal to E E minus is correct, we have written it correct, Bx Cz, we have written By Cv, dx Ez, dy Ev. Okay. Now we are multiplying this by d, therefore this dy is gone. I will have E minus dB inverse C, dB inverse C. I multiplied this by d, pre-multiplied. So this is gone. So dB inverse of C into V, and this is equal to I2. Okay. Now this goes to the right hand side, therefore V is equal to E minus dB inverse C inverse inverse. This is I2, I can throw away the I2 because I2 is multiplying by identity matrix. Therefore V is known, V is known. Now let us go to 2 or 5. Now V, therefore y is equal to minus B inverse C V. From 5 y is equal to minus B inverse C V, therefore y is known, therefore y is equal to known. Now I repeat with, I have now manipulated equation 2 and 4, I will do similarly for 1 and 3. So let us take 1, equation 1, again pre-multiply by B inverse. So we will have x plus B inverse of C Z is equal to B inverse. I have pre-multiplied this by B inverse. Now I want to throw away x from here, so I multiply this by d and subtract from there, therefore 3 minus d into, let us number it as 6. So from the equation 3 I multiplied by d and subtracted from here. So what I will again have here is E minus dB inverse C of Z, that is your E here. I multiplied this by d, dB inverse C, that is equal to B inverse. Yes, that is equal to minus dB inverse. We multiplied by d and subtracted minus dB inverse. Therefore Z is equal to E minus dB inverse C inverse dB inverse. Let us bring this minus sign over here. But this E minus dB inverse C inverse is V, therefore I can use this value of V over here and write this simply as V dB inverse. I can simply write this as this. Now solution is complete. Now use 6. 6 gives me x is equal to B inverse, I can take out common there, I minus Cz, I minus Cz. So I am using this, I have taken to this side and taken common on the left, B inverse I minus Cd. So this is your say. Now we have completed the solution of all the 4. Now what we should now see here is that in building this we have used only 2 inverses. One was B inverse, the other is, let me write it here, what we are used here is we have used B inverse, we have used E minus dB inverse C inverse. These are the two inverses that we have used in the construction of the entire system only. Now what is this order? The order of this is R into R. The order of E was S, therefore the order of this is S into S. Therefore we are now using the inverse of only two matrices R and R, S into S. Now if you go back to the example which we had written it earlier, so if you are, for example, if you are constructing the inverse of this particular matrix, what we are talking of here is that I need inverse of this, I need inverse of this, not a 100 by 100 system, but by using this, or for example in this case I need the inverse of two 50 by 50 matrices, and of course I need some multiplication of the matrices are to be done. The multiplications leave alone the extra computation. So we shall be doing enormous saving of computation in finding the inverse of large system of equations by using this particular concept, that we can partition a given matrix into a suitable form and then find out the inverse of that particular matrix using the inverses of the lower order matrices. Okay, today we shall stop at this. Thank you.